Math 1332, Chapter 2, Set Theory, Section 2.1, Introduction to Set Theory, Video 2, Ways to Represent Sets, the Roster Method, Specific Sets, and Ellipses. These things kind of blur together, especially the roster method and ellipses. But just to foreshadow, there are three different ways that we're going to talk about to represent sets. The first of which, of course, is called the roster method. So what do I mean by the roster method? Well, the roster method for representing a set simply means that you list the elements of a set in a pair of braces. Braces look like this. And so you literally just write everything out. For example, let's say that I wanted to represent the set of all vowels. Well, that would be A, E, I, O, and U. And we could argue that Y belongs in there, so we'll go ahead and put Y in there, since it can serve as a vowel in some words, such as bypass. Or we could say the set of all odd numbers less than 10. And assuming everybody knows what I mean by odd and number and less than 10, then that would be the set 1, 3, 5, 7, and 9. Now, belonging to a set doesn't have to have any requirement. In these two sets, there are very specific requirements laid out. You can name a set anything you want. In the absence of a specific name for a set, usually a name that has some meaning, we typically represent a set with a single capital letter. For example, I could say set A equals and then put anything I want in there. We could say car, truck, van, and motorcycle. But that's all roster form is. It's saying I'm going to open up a set of braces and I'm going to list everything in the set. Now, if you are writing this by hand and not typing it, it takes a little practice to draw braces fairly decently. For example, if I wanted to write a set B and inside of it put some random objects, it really doesn't matter what they are. We'll say the word key, the number 13, and I'm not picking these objects for any particular reason. Of course, in the previous example, those are all modes of transportation or vehicles, if you will, but there doesn't have to be anything that clarifies why something belongs to a set. I could put a triangle in here. I could put a Greek letter beta, if you're familiar with the Greek alphabet. And let's put dog in here as well. Now, why are these 5 elements together in the set B? The answer is because I wrote it that way. It doesn't have to have any particular reason that they're in there, but that's all roster form is. Open up a brace, list all the elements of your set, regardless of the reason that they're in the set, and then at the end, close it with a closed brace. We're going to look at some specific sets, and in the context of doing that, we'll also talk about ellipses. And you may already know what ellipses are, but let's talk about some specific sets. These are some sets that you've probably heard of before, and we are going to encounter as we go through this course. The first set that we're going to talk about are called the natural numbers. The natural numbers do have a special letter reserved for them. That would be a capital N. The natural numbers are also known as the counting numbers because they're the numbers that you would count with. So altogether, if we started counting 1, 2, 3, 4, but here's a problem. This set is not going to end anytime soon. And if we were to just close it off now, then that would not be all of them. That would just be the first 4 natural numbers. But I don't have time to write them all because they go on forever. So what can we do to say that this pattern continues without actually stopping it? And the answer is to use what's called an ellipsis, which is just really just 3 periods. But that's what an ellipsis is, or ellipsis. It's 3 dots indicating a pattern continues. That's all. Stretch that out a little bit. That might have fallen underneath my picture in the video, so we'll move that over a little bit. But that's only ellipses. It's 3 dots indicating that a pattern continues. Now, it doesn't mean that it has to continue forever. And now that I've introduced ellipses, let's go back to the previous page for a second. And we're going to write one more set as soon as I move this one down. Just drag and move that down. Let's say I wanted to make a set. We'll just call it D for no particular reason. We'll start counting. And then we're going to stop when we get to 100. Typically, when you use ellipses, it's to represent a part of a set that you don't want to write all of, assuming that you can pick up on the pattern and continue that pattern. And when you end a pattern like this one, it's usually a good idea to close it off with a couple of the elements of the set at the end. In this case, these are all the numbers, the natural numbers from 1 to 100. But you can use an ellipses in a set that has an ending by simply representing all the stuff in the middle, assuming the pattern continues. Or you can use ellipses to represent a set that doesn't end by establishing the pattern and saying, keep going forever. But getting back to our specific sets, the first specific set we're going to look at are the natural numbers. The next specific set we're going to look at are called the whole numbers. The letter for whole numbers is a capital W. And the whole numbers are just like the natural numbers, except they start at 0 instead of 1. And you might be thinking, why do they get a special name? I mean, it's just like the natural numbers. You just have to start it with 0. But if you go back and look in the history of the development of math, and specifically the development of these sets of numbers, there was a long time between the invention of the natural numbers, or discovery, that's a matter of perspective, and then the follow-up with the discovery or invention of the number 0, meaning that for a long time, the idea of a number that represented nothing, the absence of quantity, was silly. Why do we need a number that represents nothing? Well, the answer is actually quite simple. Let's say you take a test and I write this on it, and I give it back to you, and you're devastated because you thought you did well. And I say, oops, I'm sorry. I left off a 0, but it's just a 0. What could it possibly matter? So in the context of place values, you can see why the number 0 is quite important. Pause this video just for a second. All right, so let's let's continue with our specific sets. Now, the next specific set of numbers are called the integers. The integers are represented with a capital Z for the German word for integer, which I don't know. I just know it starts with a Z. But the integers are the whole numbers, but we pick up the negatives also. And because the negatives go forever, we have to start this set with some ellipses and then resume with some negative numbers like -3, -2, -1. And then we can close it off with some ellipses because it goes forever to the right also. But the integers are just your positive and negative whole numbers. 2 more sets of numbers I'd like to define. Actually, there's more than 2. And I'm going to squeeze these back in up here because really, and I'm only doing this because it's in the context of the course that we're doing right now, are the even natural numbers and the odd natural numbers. Now, in the big picture of math, these normally don't have a specific letter reserved for them, but in this class, we do. The letter we're going to use to represent the even natural numbers is a capital E, and of course, the one for the odd natural numbers is a capital O. Now, most people know what makes a number odd or even, or can recognize an odd or an even number just by looking at it. If you want to get technical, a number is even if when you divide it by 2, it has a remainder of 0. So it's evenly divisible by 2, and odd if when you divide it by 2, it has a remainder of 1. But most people know that your even numbers are 2, 4, 6, 8, etc. And your odd natural numbers are 1, 3, 5, 7, etc. But we will be referring to those later on in this course. Now there are 2 more that I'd like to introduce. The next one is called the rational numbers. And this one's a little tricky because this is where we pick up all the fractions. It's impossible to list all the fractions in order because the rational numbers, which really means ratio, so ratio of 2 integers, the rational numbers are so densely packed that you cannot list them all in order and pick up all of them. For example, let's say that you said, okay, we're going to list some fractions. So we'll start with 1/3, then we'll go to 1/2, and doesn't look like there's any fractions in between. But if we got a common denominator and change this to 3/6, actually that won't work either, and change this to 2/6, then you might think, see, there's no numbers in between. But if we got a common denominator of 12 and said that 1/2 is the same as 6/12 and 1/3 is the same as 4/12, then we can see that there's a 5/12 in between. Now, if you're panicking because I'm bringing out fractions and common denominators and all that stuff, don't panic too much. We're not going to do a whole lot of fraction arithmetic. And when we do, I'll slow it down. But the point I wanted to make was, with fractions, rational numbers, if you will, it's impossible to list them all in a row in order, because no matter how close two fractions are, you can raise the value of their denominators and eventually get their numerators far enough apart so that something will always fit in between. That property is called density, but I wouldn't worry too much about that because density is usually a topic that's reserved for upper level math classes. My point is, it's impossible to list the rational numbers. So the best thing that we can do at this point is describe them. So we will describe them by saying the set of all ratios of integers, meaning we put one of these numbers on top of another, as long as the number on the bottom isn't 0. And that's the best that we can do right now. We'll say, in other words, it's all fractions. Now, this does include the integers as well. In other words, when we say we pick up all fractions, that doesn't mean that we're losing the numbers that we had before. For example, this number 2 right here is technically an element of the rational numbers. Why? Because I can write it as a ratio of integers, 2/1. In fact, every number in here I can think of as a fraction by simply putting it over 1, which means every number in the integers is also a rational number. When we talk about subsets, we'll talk about the fact that the integers is a subset of the rational numbers. There is one more set of numbers that I would like to, a specific set that I would like to bring up, and it's called the real numbers. Oh, I'm sorry, before we move forward, the rational numbers do have a capital letter reserved for them, and that is the capital letter Q. And if you're wondering why is it Q, it's for the word quotient, which is the answer to a division problem, but a division problem is really just a fraction. As for the real numbers, the letter reserved for it is a capital R. And the real numbers is the set of all possible decimals, loosely speaking. Now, if you're kind of on top of your math game, you might remember that all fractions can be turned into decimals and decimals can be turned into fractions. But the truth is, there are some decimals that you cannot write as rational numbers. In other words, there are some decimals that you cannot write as the ratio of two integers. Without getting into too much detail, I want to go back to the rational numbers for a second and redefine them in terms of decimals. It's the set of all decimals that either terminate or repeat. And the real numbers is the set of all possible decimals, which means either they terminate, repeat, or do neither. Now, what do I mean by terminate, repeat, or do neither? Well, I'll show you what I mean on the next page. 1/2, if I can get it to draw, is a rational number. It's a ratio of two integers. And most of you know that 1/2 as a decimal is 0.5. As a decimal, that terminates, which is a fancy way to say that it ends. So that is a terminating decimal. It represents a rational number. However, 1/3 as a decimal, you might know is 0.3 repeating. And that bar means it's just a fancy way of saying the 3 repeats forever, ... So this is a repeating decimal. However, there are some decimals that neither terminate nor repeat. One of them that you might be familiar with is pi. Now, a lot of people think they know what pi is. It's 22 over 7, or it's 3.14. Both of those are approximations, but it's not really the value of pi. Pi is about 3.14159, and I'll stop writing because I'm ashamed to say this. That's the most number of decimals I know off the top of my head. But as a decimal, pi, it neither terminates, so it goes forever. Well, so does 1/3, but it neither terminates nor repeats. Now, when I say it doesn't repeat, I don't mean that the digits don't repeat, because there's only 10 digits we can use, 0 through 9. What I'm saying is that there's not an infinitely repeating pattern of decimals, like the 3 repeats in 1/3. There is no repeating pattern of decimals in pi. So if we just say rational numbers, which are our fractions or ratios of integers, then we don't pick up all the possible numbers, because those fractions are just decimals that either terminate or repeat. But real numbers is a set of all possible decimals. So it includes the rational numbers, but it also includes some other numbers that aren't rational, which also happen to be called irrational. When I say real numbers, most of you are probably familiar with this. Hey, here's a number line, 0, 1, 2 over here, -1, -2, -3. It's a visual representation of all the numbers, but this is called the real number line, because every possible number is on here. Pi is about here. 1/2 is about here. 1/3 is about there. But that's the best way to think about the real numbers. I mean, in terms of decimals, you could say it's all possible decimals, but visually speaking, it's every number on this line. So these are some specific sets of numbers that we are going to be seeing. More often than not, it will probably be the natural numbers or the whole numbers. We might peek into the integers every once in a while. Rational numbers and real numbers, we won't talk about too much in depth in this class.